Hi, I'm Zhu Jingjing from VDS Lab, Hong Kong USD Guangzhou. In this video, I will present our CVPR2023 paper, Patch Mix Transformer for Unsupervised DOM Adaptation, a game perspective. In this work, we want to address the limitation of previous works, as the performance of cursor attention highly depends on the quality of pseudo-labels. It becomes less effective when the domain gap becomes large. Therefore, we propose a new problem for UDA: how to smoothly bridge the source and target domains by constructing an intermediate domain with an effective VIT-based solution. The inclination behind this is that, compared to direct aligning domains, decreasing the domain gap between the intermediate and the source or target domain can facilitate the domain alignment. Therefore, we propose a novel and effective method called patch mix from a game perspective. Next, I will introduce our work in detail. CNN has achieved success on many vision tasks. However, they still suffer from the limited generalization to a new domain due to the domain shift problem. Moreover, due to labeling large-scale dataset is expensive, laborious, or time-consuming. Therefore, UDA is proposed to solve this issue by transferring knowledge from the labeled source domain to a labeled target domain. A lot of solutions reduce the domain gap by producing pseudo-labels for target samples. However, PR method has a limitation, as the performance of cursor attention highly depends on the quality of pseudo-labels. It becomes less effective when the domain gap becomes large. In this figure, we can see that due to the significant domain gap between the domain QD and other domains, aligning distribution directly between them performs not well. Therefore, we propose a research problem: how to smoothly bridge the source and target domains by constructing an intermediate domain with an effective VIT-based solution. I first introduce patch mix. Patch mix is designed to interpolate the case source patch and target patch to reconstruct a mixed image with n patches. This is the formulation for our proposed patch mix. This figure shows the difference between our proposed patch mix and other mix-up method. Please note that we unified the global and local mix-up in our proposed patch mix module. We interpret UDA as a minimax C game among three players, namely the feature extractor, classifier, and patch mix module. Feature extractor and classifier aims to minimize the CE loss, and the patch mix module aims to maximize the CE loss. The equilibrium states each player's shrinkage is the best response to other players, and point omega hat is Nash equilibrium if the cost meets the condition. In our case, NE means that no player has the incentive to change its own parameters, as there is no additional payoff. PM trans consists of three players: the patch mix module and the VIT encoder and the classifier. Patch mix module is proposed to construct the intermediate domain. The patch embedding layer in patch mix transforms input images from the source or target domains into patches, and the VIT encoder aims to extract features from the patch sequence, and the classifier maps the outputs of VIT encoder to make predictions, each of which is utilized to select the feature maps to reweight the patch sequence. The patch mix with a Limbo beta distribution aims to maximize the CE between the intermediate domain and the source or target domain. After we propose patch mix module to maximize the CE loss between the intermediate domain and the source or target domains, we propose semi-supervised mix-up loss to minimize the CE loss. In the label space, we utilize supervised mix-up loss to measure the domain divergence based on the CE loss. This is the formulation for CE loss in the label space. And in the feature space, we propose to minimize the discrepancy between the similarity of their features and the similarity of labels in their feature space. And this figure shows the illustration of two proposed semi-supervised losses, and this is the CE loss between their label space. This is the CE loss between their feature space. The minimax C game aims to align distributions in the feature and label space. We utilize the random mix-up radio from a limbo byte distribution in our patch mix model to maximize the CE loss between the intermediate domain and the source or tag domains. Moreover, the feature extractor and the classifier has the same objective to minimize the CE loss. The total objective of PM-trans is defined as: after optimizing the objective, the patch mix model with the ideal byte distribution will not maximize the CE loss anymore. Meanwhile, the feature extractor and the classifier have no incentive to change their parameters to minimize the CE loss. Finally, the distribution between the intermediate domain and the source or tag domain is nearly zero, further indicating that the source and the tag domains are well aligned. We show some experimental results on 4 datasets to demonstrate the effectiveness of our proposed PM-trans. PM-trans can get more robust transferable representations than the CNN-based and VLT-based methods. On the Office 31 dataset, PM-trans achieves the best performance on each task, and outperforms the peer SOTA methods with same backbones. On the VSD dataset, PM-trans also surpasses the SOTA methods on several subcategories. On the most challenging DomainNet dataset, PM-trans outperforms the SOTA methods and surpasses the SOTA methods in all the 30 subtasks. This figure shows PSN visualization. Compared with Swan-based and PM-trans Swan, our PM-trans can better align the two domains by constructing the intermediate domain to bridge them. There are some evidence studies about our proposed PM-trans, like effect of semi-supervised loss, effect of learning parameters, and effect of PM-trans compared with local and global mix-up method. We propose a novel method PM-trans for UD from a game perspective. PM-trans achieves the SOTA results on 3 datasets. We plan to implement our patch mix and the two semi-supervised mix-up loss to solve self-supervised or semi-supervised learning problems or other challenging downstream tasks like semantic segmentation and detection. Thanks for your listening.